Now you have, and I'll just give you a brief idea that after this, we're done with atomic structure and chemical bonding. We're going to continue with organic. I mean, inorganic or organic. Inorganic is mostly memorization, so we won't be spending a lot of time. I'll just give you notes of inorganic, and we'll go through them, and you will mostly be just memorizing stuff. So inorganic is not an issue. Once we're done with atomic structure and chemical bonding, we will continue on with organic. Um, Now, ionization energies, we talked about first ionization energy, which is it's energy needed to remove electrons from an atom, like 1 mole of electrons from 1 mole of gaseous atoms. That's the first ionization energy. You had second. The seventh was that 6 electrons are already removed, and you're trying to remove the seventh one now. So, so that was ionization energies, and the factors that affect ionization energies are that the first one is the number of protons. More protons, there's more attraction for electrons. So electrons, it would be more harder to remove those electrons. The ionization energy is going to be higher. Then you had the distance of the electron from the nucleus. Like if the electron is really far away, it would be easily removed. It's going to be lower ionization energy. Not a lot of energy would be needed to remove that electron. Then you had a shielding effect, which was the number of electrons in the inner shell. That was shielding effect. Like the outer electron you're trying to remove, and the nucleus, there would be a bunch of electrons that would be coming in the way. They would shield the nucleus. I mean, the positive nucleus will not be able to attract the electron on the outside because there are lots of inner shells which would be blocking the force of attraction. So in the case of iodine, the shielding effect is very large. So iodine is probably going to be able to lose electrons very easily. So you had shielding effect, that's a number of inner shell. More inner shells, it becomes easier to remove electrons and less energy is needed. And then you had the net positive charge. Now the next, uh, the fifth factor, we did not really discuss that much. So we talked about successive ionization energies. We did that, like removing the first electron, that's kind of easy. I mean, the first 2 electrons are kind of easy because they're really far away. So they have a lower ionization energies, but removing the third to the 10th electron, I mean the third, fourth, fifth, sixth, seventh, eighth, ninth, 10th electron, I mean these inner shell electrons becomes harder because they're closer to the nucleus, and the shielding decreases, the distance decreases, so they're more strongly attracted, so removing them becomes slightly harder. And removing the last 2 electrons, that is very difficult because the distance decreases even further and they're even closer to the nucleus. So removing the last 2 electrons becomes even more difficult. So by looking at and why is there a constant increase? Because every time there's a net charge, positive charge that increases. Every time it loses electrons, the ion becomes more positively charged, which is why it successively, even if nothing is happening, it successively becomes harder and harder to remove electrons because of the constant increase in this net positive charge. As anyway, so by looking at the electronic configuration, you can figure out that these 2 electrons were very far away. These 8 electrons were close to the nucleus. These 2 electrons were very close to the nucleus. So you can get an idea about shells. I mean, this is how they figured out that which electron is at a higher energy level. I mean, this is a shell number 3, this is shell number 2, this is shell number 1. From this, people figured out that electrons might not all be very close to the nucleus. Some would be very far away, some would be very close to it. And you can figure out the valence electrons, like which electrons are really far away, which is why it becomes easier to remove them. You can figure out the total number of shells. So you can figure out a lot of things based on. So we did past paper questions on this as well. So I'll just, this was fluorine. First, sixth, this is oxygen actually. I'm not really sure, but I think this is oxygen. Removing the 6 electrons was easy. Removing the 2 initial electrons kind of becomes difficult. So anyways, is this all clear? We did past paper questions on this as well. Is this clear to everyone?
Yes.
Yes, sir.
So now the next thing that we're going to talk about is we're going to start comparing just the ionization energies. We're going to start comparing uh, the first, and now we're comparing ionization energies of different atoms. Now, previously, we took an atom, we started removing electrons from the same atom. Now, what we're doing is we're just comparing the first, like how difficult it is to remove the first electron. So, we're going to compare first ionization energies down a group. So, what happens when you move down a group? For this, I'm just going to pick. I'm going to pick magnesium. Let's say group 2, and we can have. So that's my magnesium atom, and I'm going to pick calcium, and there's a beryllium atom as well. So let's. So let me just copy those atoms very quickly. So we've got a beryllium atom as well, and I think it's this one. As anyway, so I'm gonna copy this. This is magnesium. So that's the first one, magnesium. Let's copy beryllium. And then you had calcium as well. So 3 atoms down the group. So can you just hold on one second? Let me take this call. Sorry, can you hear me?
Yes, sir.
So we're moving down a group. And remember, we're only comparing the first ionization energy, which is basically we're trying to remove just one electron, which is going to be this one, this one. Okay, I'm marking all those electrons. I'm trying to remove these 3 electrons. So how difficult it is going to be if I try to remove uh, one by one, okay, comparing them. By just looking at them, which one do you think is easier to remove? Is it going to be this one or this one? What happens down the group?
Calcium.
Which one?
The one with lots of shells.
Okay, so this one would be easy to remove electrons. So what happens is that ionization energies, I mean that's what's happening, ionization energies, they decrease down the group. It becomes easier to remove electrons. Okay, so you'll be specifically, and this happens in all groups. So it's going to be a very typical question that will be asked. What's the factor? I mean, explain why does it become easier? Factor number 1. Why is it easier to remove this electron?
Because the protons is like weaker attracting the outer electrons because of the shells in the middle in between.
So there's more shielding. That's one. That's shielding effect. I mean, there are lots of things that are coming in the middle. So the nucleus will not be attracting the outer electron. So that's one, shielding. What about the other one?
It's farther from the nucleus, so it's more easier to remove.
So one is you've got more shielding, more inner shells when you go down the group. So you got more inner shells. The other one is distance increases, or you can call it the atomic radius increases. I mean, you can call it distance as well. So, because of these factors, ionization energy decreases. It becomes easier to remove electrons. There's one factor that actually goes against this. What is that one factor? Like when you move down the group, I mean, obviously the electron is further away, it's more shielded. So, because of these two factors, it becomes easier to remove electrons. There's one factor that actually goes against this. What is that one factor? Okay, that is because when you move down the group, the proton becomes, I mean, you've got more protons. Over here, you have lesser protons. In calcium, you've got 20 protons. That's a lot of protons. So there's one factor that says that does the opposite because you've got more protons, so the electron must be more strongly attracted. But since two factors are opposing this fact, so ionization energies decrease, but you have to state this in your answer, despite the fact that protons or nuclear charge increases. So there are two factors that are outweighing this one factor. Okay, is this clear to everyone?
Yes, sir.
Okay, Hani, is this clear? Anna, is this clear? Alicia, Aisha, is this clear?
Yes, sir.
Asha, so remember this. It's a very typical question that is asked very frequently. What happens to the first ionization energies down a group? They decrease down the group. Why do they decrease? Because you got more shielding, more inner shells, and the atomic radius increases. So ionization energy decreases, but you have to always add this fact that despite the fact uh, that protons increase. Okay, you can correct my grammar. I'm going to, so more shielding, atomic radius, and the last one is protons. That's the one that goes against it. So that's it. That's it down the group. You guys get this question, you answer this. The next one is what happens across the period. So it's the comparison of first ionization energies across the period. Mahad, are you there?
Yes.
Achha. Achha, first ionization energies across the period. So does it become easier to remove electrons? Does it become difficult to remove electrons? I think I did copy the atoms across the period somewhere. So I think it was this one. No, not this. Across the period. I said I'll just copy this again. So when you move, so now when you move across the period. So I've got, I mean the elements missing. I just wanted to show you the trend. It's lithium. I'm going to add the missing elements as well, which are, you've got lithium, then beryllium, then you have boron. That's group 3. Then you have got carbon, then you've got nitrogen, oxygen. Carbon, group 5, then oxygen, group 6, fluorine, group 7, and then you've got neon, I think, neon. So those are your, I've only drawn lithium and carbon and neon. So not neon, I actually have drawn fluorine actually. Okay, but you'll get the trend, you'll understand the trend, what's going on. And I'm going to rub these off. So anyways, you'll understand what the trend is. That when you move across the period and when you move to the right of the period table, uh, so we're trying to move in this direction. Let's talk about the factors first. The first thing is, if you look over here, you're getting more protons. Like lithium only had 3 protons, carbon over here had 6 protons, fluorine has 9 protons. So steadily the number of protons, they continuously increase. You have 4, 5, then you've got 6, then 7, 8, 9, and 10. So you got more protons, right? So there's more protons, which indicates, I mean, there's more nuclear charge, which increases a stronger attraction for electrons, right? Is this clear to everyone?
Yes, sir.
So fluorine over here, because it has 9 protons, there's a lot more positive charge over here. So the electrons would be very tightly held together by this larger nuclear charge, which is over here. So there's going to be stronger attraction for electrons, and that would result in greater ionization energy. It becomes more and more difficult to actually remove electrons. That's factor number one. You've got across the period, you've got more protons, right? What about distance? What happens to the distance? Is there any change? I mean, you're trying to remove the. Remember, it's the comparison of the first ionization energy. So you're just trying to remove the first electron. So I'm just marking that single electron. So in all these cases, I'm trying to remove only one of the electrons from the outermost shell. So what happens to the distance? Is it changing or not? Anyone, is the distance constant or is it changing?
It's constant.
Constant.
Okay, so it appears to be constant, but it actually slightly decreases. Distance, I did explain this earlier. The distance slightly, or you can call it the atomic radius slightly, slightly decreases. There's a gradual decrease, and the explanation for that was that you've got more protons, right? So the outer electrons are going to be very strongly attracted. Because of the stronger attraction, the nucleus is more positively charged. Because of the stronger attraction, the electrons are going to be very tightly. One second. So they're going to be very tightly held together. So the atomic size would actually be smaller, slightly smaller. It's not going to be a huge difference. But as you go across the period, the distance gradually. I mean, this would hardly be attracting its electrons, so it would be bigger in size. Fluorine, because of its 9 protons, would be very strongly attracting its electrons. So the distance gradually decreases. Is this clear?
So
Yes, sir.
would the
Yes, sir.
fluorine one be really less?
Can you repeat? What's your question?
Would the fluorine atom's distance be lesser than lithium?
Yes, because it's got 9 protons, right? So I mean, all of them have 2 shells, right? But if you have 9 protons, you will be attracting your electrons really, really strongly. Anya, is this clear?
Yes, thank you.
Okay. I mean, otherwise, by just looking at the shells, it would appear that they are the same, but the distance gradually, slightly decreases. We did this earlier as well, from where I copied this. Okay, when we were talking about atomic sizes somewhere up above, I told you across the period, I made a graph as well. Like they appear to be the same, but they're not the same. It's actually every time a proton increases, the atom's atomic size kind of slightly decreases because of the stronger attraction. The electrons are a lot closer to the nucleus. So remember this: down across the period, the atomic radius constantly decreases. But it's a gradual decrease, not an abrupt decrease. It's a very gradual change. So that's factor number two. And then you've got a third factor, which is not a factor in this case. The shielding is the same. Like this electron and the nucleus, it has two electrons coming in the way, right? This electron and the nucleus, it still has two electrons. So the number of inner shells are the same. So that is not going to play any role. So same number of inner shells. So this thing kind of indicates that you have constant shielding. Now the other factors, they don't really matter because the fourth factor was the net charge on the atom. In all this, they're all neutral. You're just trying to remove the first electron, so that's not a factor over here. And the fifth one, we didn't even study the fifth one, so you can ignore that for now. So anyways, you're going to have a greater ionization energy because of these three things. Constant shielding, distance slightly decreases, but the number one reason why you have an increase in ionization energy is you always get more protons, right? When you move to the right. So remember this as well across the period. Okay, across the period, you have this going on. But also remember this is known as the general trend. So this one is known as the general trend. Make sure you know this. Make sure you know the reasons. I mean, it's not that difficult to remember, but do make sure you know all the factors that are going to matter when you move across the period. I say, is this clear to everyone?
Yes.
So now we're going to be a bit more specific. Now the thing is, and this is, I'll just copy a graph instead of making one. Just a second. So when you move to the right, it increases. This one is better. So now we're being more specific, right? So now we're being just one second. So now we're being more specific. This first one is period number. It's period number 2. Okay, that's the second period, period number 2. And then you have the next period. That's period number 3. So the general trend across the period is the same. I mean, it is following the general trend, which is. Sorry, one second. I say it is following the general trend, which is that you get greater ionization energies. I mean, don't compare the periods yet. Just focus on one period across the period. I mean, you can check the trend is the same. Okay, we're not comparing the two periods. We're just comparing that period number 2, same trend. Period number 3, same trend. But there's an issue. If you want to be specific, you would notice that there is something going wrong over here at boron and at oxygen. They're not following the trend. Something wrong with aluminium and sulfur as well. So basically, there are dips at group 3, and there's a dip at group 6 as well. Similarly, over here as well, aluminium is in group 3. It's in the next period. And sulfur is in group 6, which is also in the next period. If it would be better if we have a periodic table in front of us as well. Just a second. I said this one. So from this point, from lithium to neon, the general trend is it's increasing, right? But there are going to be dips at boron, group 3, and a dip at group 6. Same is true for period number 3. Sodium to chlorine to argon, there's going to be an increase, but there's going to be a dip at aluminium and a dip at sulfur. Okay. So we're now going to talk about, we've already talked about why there's a general increase, right? Now we're going to talk about why is there a dip at group 3 and why is there a dip at group 6. So what went wrong at group 3? So we're going to try and learn how to explain this. So what goes wrong at group 3? Now the thing was that if you, now we're being very specific. Now the thing was that you had all these atoms, right? And I'm going to write the, or just copy them. So I've copied all of them here. We did learn that they had the same number of shells, everything, etc. Almost pretty much everything was the same. The only difference was remove this. Now we're going to talk about the fifth factor actually, which is that orbitals, etc., they do matter. And why do they matter? So here's what's happening. Lithium has 3 protons, right? It's got 3 protons, it's got 3 electrons. The electronic configuration is going to be, if I write them vertically, it's going to be 1s, 2, and then the second shell will have 1 electron, right? Beryllium, you reach group 2, same electronic configuration. It's going to be 1s2, and then it's going to be 2s2. That's it. When you reach boron, that's group 3, right? So why is there going to be a dip? It's going to be 1s2, 5 electrons, 2s2, and then there's going to be 2p1. Now, all of a sudden, what happened? When you move from group 2 to group 3, there's a thing that changed. Like, group 1 and group 2 were following the trend because the orbital was the same. They were removing electrons from the same orbital, right? They had exactly the same electronic configuration. The electrons were exactly in the same orbitals. So that was not a factor. But as soon as you moved to group 3, all of a sudden it became easier to remove electrons. So why did it become easier to remove electrons? Because now you're removing electrons from an orbital which is slightly further away. So the explanation for that is that the electron in group 3 is removed from a higher energy p orbital, which is slightly further away. Like the 1s and 2s were much closer. The 2p is kind of slightly further away, just a tiny bit. So electron in group 3 is removed from a higher energy p orbital. Is everyone following me? Okay, the electron is much further away. Is this clear?
Yes, sir.
I mean, otherwise, these orbitals don't really matter that much. But the reason boron, it became easier to remove electrons because the electron was from an orbital. Because otherwise, you don't actually go into a lot of detail when you discuss ionization energies. You don't mention about orbitals at all. But over here, there's this tiny dip that's coming in. That's because of electron being removed from a much higher energy p orbital. Is this clear?
Yes, sir.
ठीक है, Anna, is this clear? Aisha, Hania, Mayam, is this clear?
Yes, sir.
So electron in group 3 is removed from a higher energy p orbital, which is further away. So it's further away because it's I mean the 1s would be close to the nucleus, the 2s would be after that, and then you've got the 2p, which is going to be slightly further away, which is further away and also more shielded. So and also has more shielding as well. Because the 2p, the nucleus was already covered by the 1s and the 2s electrons. So the 2p is much further away. It comes after that. So there's more shielding. The nucleus is already surrounded by two orbitals. I mean, compared to the 2s, like the 2s, the shielding is lesser. There's only 1s orbital surrounding the nucleus. So the 2s would come after that. These electrons would come after that. So the shielding is lesser compared to the 2p. So it also has more shielding, and you all compared to the group 2 element, where electron is removed from a 2s orbital or a 2s subshell. Over here, I'm going to mention subshell as well. I mean, orbital is also right because the p subshell has the p orbital, so that would also be correct. But that's your explanation, which you have to remember. It's a very I mean, they like this question a lot. This particular question comes very, very frequently, and you have to explain why is there a dip, why is the trend not being followed by this group 3 element, because all of a sudden it became kind of easy to remove electron. The electron went into an orbital which was further away and also more shielded as well. So is this clear?
Yes, sir.
ठीक है, rest is everyone, is this clear?
Yes, sir.
Rubab, is this clear? So next is you've got so what about, there's another dip that's happening at group 6. Okay, so we need an explanation for that as well. Dip at group 6. Why is it becoming easier to remove electrons at group 6? And so what happens at group 6? So now after this, the electronic configurations are kind of exactly identical. Like you've got carbon. So every time the electron, so the orbitals are not going to be a factor because every time it's going to be the same electronic configuration. It's going to be 1s2, 2s2, and then it's going to be 2p2, right? So pretty much the same. So orbitals, if you're comparing these two, orbitals would not be a factor because you're removing electrons from 2p, you're also removing electrons from 2p over here as well. So that's not a factor anymore. Then you've got 1s2, that's 7 electrons, 2s2, and then it's going to be 2p, 3. Again, not a factor. And then you reach group 6. And at group 6, something happens. It's going to be 1s2, 2s2, and then it becomes 2p4. I'm going to write the other electronic configurations as well, 1s2, 2s2. Now the 2p subshell is not changing, so orbitals should not be a factor anymore. This would be 1s2, 2s2, and 2p6. But there's something going on when you move from nitrogen to oxygen. All of a sudden it became easy to remove electrons. So what's the difference between 2p3 and 2p4? The difference is that when you were trying to remove electrons from the nitrogen atom, the electronic configuration was 1s2 and 2s2 and 2p3. 2p3 means that the 2p orbitals 2px, 2py, and 2pz, they were all having one electron each. And that means, like, if I draw the 2p orbitals, okay, so you have this. If I draw the 2p orbitals, there were electrons that were lying on the x-axis, there were electrons that were lying on the y-axis, and there were a bunch of electrons that were lying on the z-axis. But all these electrons were occupying different orbitals. You had an electron over here. I mean, there was an electron that was buzzing in the, let's call it the 2pz orbital, right? There was an electron that was in this green region over here that was buzzing around in this area and occupying the whole area. So just like a bee, it was buzzing around. And there was an electron that was on the y-axis. So all the orbitals were filled, but they were all separate. I mean, this orbital had nothing to do with this orbital. So they were all in their separate places. There was no repulsion. So all the electrons had minimum repulsion. But when you move to oxygen, which we did over here, it became 2p4. So in oxygen's case, the electronic configurations were kind of the same, except that now you had 4 electrons in the 2p. Now the thing is that one of the orbitals had 2 electrons. So imagine this one having 2 electrons, like this region, the red one had 2 electrons. The 2 electrons are going to repel each other. And if they're going to repel each other, I mean, this would repel, the other one would also get repelled. So it would become easy to actually remove electrons. So there's going to be mutual repulsion. And it becomes easier to actually remove electrons. In the previous case, there was no mutual repulsion because the electrons were occupying separate regions. One was over here, one was over here, one was over here, like 2px, 2py, and 2pz. So they were all in separate places. But now you have the same place with 2 electrons. So the electrons would be trying to knock each other out. So it becomes easier to actually remove the electron when you move to 2p4. Is this clear?
Yes, sir.
Okay, Baki, Mayam, is this clear? Anna? Mahad, is this clear? Nabila, is this clear?
Yes. Yes, sir.
Hania, all clear?
Yes, sir. Clear.
Acha.
Yes, sir.
Acha, so what? So you're going to phrase your answer properly. Okay? I mean, this is a very typical question that is almost asked in every paper. So you're going to phrase the answer. So in group 6, what happens is the first thing is you're going to explain that in group 5, whatever the element is, nitrogen, in this case, electrons are removed from a half-filled p subshell. P subshell. While in group 6, which in this case is oxygen, we're talking about oxygen, electrons are removed from a paired p subshell. So the same orbital now has 2 electrons. And this mutual repulsion, like if the same orbital now has 2 electrons, the mutual repulsion of the electrons, that's known as spin pair repulsion. So due to spin pair repulsion, in oxygen, in group 6, in oxygen, it becomes easier to remove electrons. Hence, you have a slightly lower ionization energy. And you have to remember this particular explanation as well. The dip at group 6 and the dip at group 3 always happens whenever you have any whenever you move across any period in the periodic table. There's going to be a dip at group 3 and at group 6. And remember these two reasons, right? In group 3, you all of a sudden are removing an electron from an orbital which is much further away, and it's also more shielded. What happens when you move from group 5 to group 6? Previously, all orbitals had one electron in them. Now, all of a sudden, one of the orbital has two electrons in them. So because of the two electrons trying to knock each other out, repelling each other, it becomes easier to remove electrons. So, is this all clear?
Yes, sir.
So, let's continue. We're done with ionization energies. There's just a few minor points that I would have to explain about comparing these trends across the period. But we're done with most of the ionization energies. We'll do past paper questions on ionization energies in the next class then. Okay. Today, everyone, I'll share the board as well. Okay, take care. Anyone has any questions?
No, sir.
Okay then. Take care.
Thank you,
Allah.
sir.
Allah
Allah
Hafiz.
Hafiz.
Allah Hafiz.
Allah Hafiz.